Okay, so in this particular lecture, we are going to be looking at some growth rate models. So let's go back and look at that first one. It reads, between 2006 and 2016, the number of applications for patents, and they're calling that N, grew by about 3.2%. Okay, so no problem, understand that. That is, N prime of T is equal to 0.032 multiplied by N of T. So remember, whenever we see the derivative, that means we're actually dealing with what? Yeah, we're dealing with the rate of growth. So they're telling me that the rate of growth is the percentage, the growth percentage, 0.032, multiplied by the actual function, N of T. Cool? And like, how can that be possible? Just hang in there a second. We'll see. And they're giving us a part A to work with. So part A says, or asks actually, because they want us to find a function that satisfies this equation. And they're giving me some information. Okay, so I need to find a function. And the information they're giving me that at time equals 0, we're talking about the year 2006. And they say there's approximately 451,000 patents that were received, or patent applications that were received. So that's 451,000 that were actually received. Now, since this is a growth model, because they told us that the number of patents grew about 3.2% per year, that means we're dealing with the formula for a growth rate. Now, the formula I always use looks like this, right? It's actually the compound formula, right? Continuous compounding formula. Agreed? Now, P usually stands for population. Remember, when you see a variable with a sub-zero, that's always the initial amount. We can put n's in place of those p's, whatever variable we want to use, it's not a problem. But we usually leave this as k for the rate and t for the time. Cool? Okay, now here's the deal. They want us to find an equation that actually is going to satisfy this growth rate model. Well, if I'm going to find that n of t, so let me just replace this. Instead of p, we're going to call it n of t. And this is going to be n sub 0, which means the initial amount. In order to find this n of t equation for growth rates, just like for continuous compounding in the finance world, there's two pieces of the puzzle that we need. We need to know the initial amount, which in this case is represented by n sub 0, and we need to know the rate, which is represented by k. So answer me this. Did they give me the initial amount? Like, I'm not sure. Well, go back to what we wrote down for part A. They said at time was 0, they received 451,000 applicants or applications. Did they give me an initial amount? They certainly did. Time is equal to 0 means that my initial amount is 451,000. So in this case, I've got it. This is 451,000. Did they give me a rate? You're like, well, go back to the beginning of the problem. What did they tell us in the very beginning of the problem when we read the little blurb before part A? Yeah, in the very beginning of the problem, they said it grew at about 3.2% per year. So did they give me a rate? They certainly did. They told me 3.2% per year, right? So, do I actually have all the pieces of the puzzle to write this particular n of t function? Yes, I do. So, in this case, n of t is going to be equal to 451,000 times e. Now, do I use 3.2%? Good, you don't. Because just like the finance world, you don't use it as a percentage, you use it as a decimal. which means 0.032 multiplied by t, which is time. So there's my function, n of t. And as we should do in this case, we should actually check our work to make sure that when we take this derivative, we end up with that original derivative that they gave us. You with me? Okay, so to do this, we are going to look at, and by the way, this is to check our work. I am going to take the derivative of this function. So, remember how to take the derivative of a function that has an e in it. Good. To take the derivative of a function with an e, it is itself, isn't it? So that means it's going to be the 451,000 multiplied by e to the 0.032t, and then what? Yeah, multiplied by the derivative, in this case with respect to t, of the power. Right? Okay, so what's the derivative of 0.032t? Yeah, just 0.032. So this derivative, if I take a look at it, this part right here, this first part right here, what is that what can I represent that by? Yeah, isn't this just the n of t? Good. So I could actually just write that first part as n of t. And this second part, yeah, what did we say the derivative of that was? Good. 0.032. Isn't this exactly what they gave us up there in the beginning? Awesome. Okay, so we checked it. We did it correctly. Our n of t function in this case is given to us right here. And I'm just going to box it up to make it a little more obvious for us. Cool? Good. All right, now part B. Part B wants to know the number of patent applications in 2021. So let's think about this a second. They want the number of patent applications in 2021. Am I dealing with the derivative or am I dealing with the original function? Good. They didn't want the growth rate. They said they want the actual number of patent applications, which means this is the formula that I'm dealing with. Because this represents the number of patent applications at time t. Now, the year is 2021. Is t going to be 2021? Good, it's not. And some of you are like, well, how do you know that? Well, look at part A. They told me in the year 2006, t was equal to 0. So if in 2006 t is equal to 0, then in 2021 t is equal to 15. Because 2021 is 15 years later, right? Okay, so the number of patent applications in 15 years is going to be found by taking this 451,000 times e to the 0.032 multiplied by 15. Got it? Okay, so I know you got your calculators out. Get your calculators out. I got my answer already. Let's see if we agree upon our answers. And if we don't, that means one of us did the wrong finger punching work, right? So let's see. I ended up with, and I'm rounding to the nearest whole number because you can't have a partial patent. I ended up with approximately 728,850 patents. Or not patents, but patent applications. So let me get rid of that S there. Good? Okay. Loving it. Let's see. Part C. Estimate the rate of change in the number of patent applications in 2021. So now they want the rate of change, which means, what are we going to look at? Yeah, we're going to look at the derivative, aren't we? Well, if I'm going to look at the derivative was written n of t equals 0.032 times n of, right? The derivative was equal to 0.032 times the original function. And we proved that over here. When we checked it, we proved it right here. So they want to know they want us to estimate the rate of change in the number of patent applications in 2021. So time is what? Good, 15 years. So we are just going to take the 0.032 and multiply by n at 15 years. Well, didn't we already compute that? Yeah, that answer's here, isn't it? So, gratefully, this part C isn't as big of a deal as it could have been. Okay, got your handy dandy calculators? Good, so do I. So the change in patent applications at 15 years is, what did I get? I got approximately, and again I rounded to the nearest whole number, 23,323 patents or patent applications, right, per year. Cool? Does that make sense? Not too bad, right? Gratefully, since this is a growth model, this is the formula that we use. And again, the p can be changed to n or whatever the variable they want to use. But since it has the function e in it, when you're talking about its derivative, it's just itself multiplied by the power, derivative of the power. So this actually made this problem very simple when we realized, oh, we're dealing with an exponential function. Oh, derivative is its, oh, not too bad, right? Cool, hang in there. Got another example. Okay, let's look at the next one. It reads, the size of a certain insect population is given by this particular function, where t is measured in days, right? And they want to know at what time will the population actually equal 600. Okay, so what are we looking for here? Yeah, we're looking for the ending population, aren't we? And so time is in days. It's always good to make that note for ourselves. T is in days. And they give us the ending population we decided. And that was 600. We're dealing with mosquitoes? Nope. Just an insect population, whatever that means. Okay, so how are we going to set it up? Good. We're going to write 600 equals 100 times e to the 0.02t. Right? Loving it. All right, then what? Good. Solve like we did before, right? We've done these before. Divide both sides by the 100. And then what? Yeah, take the natural log on both sides, and gratefully on the right side, the e will drop out. And then divide by the 0.02. So now I know most of you have your calculator out and you are doing your work. And they say round to 1 decimal place. So let's see. Pause the video if you need to, but this is what I got. I got that, and when I rounded to 1 decimal place, it bumped it over. So I actually got the time was 90 days. It was 89 point something, but that like something was above 5, and so when it got rounded, it rounded it to 90 days. Hopefully we agree. Do you agree? Cool. Stay tuned. Got another one for you. Okay, ready for another one? It says, suppose that in 1648, a man bought a diamond ring for $12. That was expensive. Suppose that the man had instead put that $12 in the bank at 3% interest compounded continuously. What would that $12 have been in 2004? Okay, so this is a continuous compounding formula, isn't it? All right, so this is a pretty straightforward problem. They're asking for a dollar amount, so we need to remember that formula. The ending balance is equal to, right, the initial amount multiplied by e to the r times t. Cool. Okay. Well, what else do we know? The 3%. So we've got a 3%, and it's positive, so it's clearly a growth rate, isn't it? Okay, so if they want to know the ending balance, that means I need to know the initial amount. Do I? Good, $12. Rate, yep, 3%. Time. Uh-oh. What's the time here? Yeah, I need the time is going to be the difference between 2004 and 1648, isn't it? Okay, so assuming we've both done our arithmetic correctly, I have time being 356 years. That's a long time for the money to be put in the bank. That is a, hey, we're going to will this to the next generation type of thing. All right, so our ending balance is going to be found by the initial amount, $12, multiplied by e to the, good, 0.03, multiplied by 356 years. So since it's money, I shouldn't have to tell you what decimal place to round to, should I? All right, give you a few moments. Pause the video if you need to so you can do your finger punching, and then come back and let's see if the two of us agree. Ready? Okay. I got $521,730.60. And yes, I want my 60 cents. Did you get the same? Awesome. Gratefully, this problem was a simple one. Stay tuned. Got it. All right, so let's look at the next one. The next one reads that the number of women graduating from four-year colleges in a particular country grew from 1930, all right, so the year is 1930, when 48,684 women earned a bachelor's degree, to the year 2007, when approximately 740,000 women received such a degree. They would like us to find an exponential function that actually fits the data. And then they want us to find the actual growth rate. Okay, so here's our information. In whatever country it was in 1930, 48,684 women actually received their bachelor's degree. And in 2007, 740,000 women received the bachelor's degree. Cool? They want us to find an exponential function. Okay, so since they want an exponential function, it's time to write down the generic formula. So here's my generic formula. Again, remember the p's could be whatever, n's, whatever. It's just the format of it, right? Remember, this is also modeled off of the compound continuous formula, yes? Okay, so to write a function, we need, what do we need? Good, I heard you. The initial amount, and what else? And the rate. Okay, so my question to you is this. Did they give us the initial amount? Yeah, they did, because they started telling us in 1930. So that means this time is 0. So here's our initial amount of the 48,000, right? Okay, and then we need the rate. Did they give us the rate? No, as a matter of fact, that was one thing they said to go find. So we need to find K. Need to find K. All right, so K must be the only variable. We have the initial amount. We said it was that 48,000. What do you think the ending amount and the time is going to be? Yeah, the ending amount is definitely 740,000. But what's the time? Good. The time is between 1930 and 2007, which is, stay off the calculators. How many years is that? You're like, how do you get that so fast? Well, what's 1930 to the year 2000? Good, 70 years. And another 7 on top of that. That's how you can do it so quickly without using the calculator. Good? Okay, so now, since we need to find K, we know the time is 77. We know the initial amount was the 48,684. And we know the ending amount was the 740,000. So, ready to plug it all in? Loving it. So, 740,000 is equal to the 48,684 times e to the 77k. All right, what are you going to do first? Good, divide by that 48,000. Oops, I forgot 740,000. I forgot 1 0. Always good to check your work. E to the 77k. All right, how do I get rid of that e? Because I need the k by itself. Natural log on both sides. I heard you. Okay, so I've got the natural log of this lovely fraction. 740,000 divided by the 48,684 equals what? What's on the right? Good, 77k. And then what? Yeah, divide both sides by the 77. Okay. So you do your work. I'll do mine. Round to 3 decimal places on that k. And pause the video because I already got my answer. Got it? Okay. I got 0.035. That's what I got. Did you get the same? Yay! All right. So that means our specific function. Remember, to write the specific function, what pieces of information do we need? We need the initial amount and we need the rate. Well, we've got the initial amount. So they use the variable n here. So n of t equals the initial amount, 48,684, times e to the 0.035t. Cool. How are we doing? So far so good? Loving it. Stay tuned. Got another. All right, so let's look at the next one. It told us in 2004, an art collector paid $66,303,000 for a particular painting. That same painting sold for only $31,000 in 1950. You're like, that's cheap. Yeah, but you got to understand, in 1950 dollars, $31,000 is extremely expensive. Okay, so they give us a few parts they want us to find. So let's look at the first part they're asking us to find. They're asking us to find the exponential growth rate to 3 decimal places, and they want us to find the specific growth rate function v, for which the v of t is the painting's value in dollars after 1950. T years after 1950. Okay, so they want us to find a growth model, right? And in this case, they're asking us to use v for value, and we're finding the value at time t. Well, since it's a growth rate, that means that this is our standard generic formula for a growth rate, right? Now, to find the specific formula, right? To find the specific, how many pieces of information do we need to know? Yeah, 2. We need to know what? Good. The initial amount. And we need to know Good, the rate. So question, did they give us either one? Oh good, they gave us the initial amount, $31,000, but did they give us the rate? No, as a matter of fact, that's the first thing they're asking us to find in this particular part, isn't it? All right, so if I need to find K, that means I need every other piece of the puzzle. Not only do I need to know the initial amount, but I need to know the time and I need to know the ending value, don't I? Okay, so the initial amount I know we have. The question is, do we have the ending value and the time? Well, good. Since the initial amount was $31,000, that was kind of obvious, right? The ending amount was at $66 million, but what about the time? Yeah, you're like, well, right. After 1950, which was the initial time, this is where t was equal to 0. How much time is it from 1950 to 2004? Don't use the calculators. What'd you get? That was 54 years. So this is time being 54 years. 54 years after 1950 is the $6 million. That's where we get that. So in this case, your ending value is the $66,303,000, and that equals, good, the initial value, which was $31,000, multiplied by E, and I don't know the K, but I do know the time, good, 54 years later. 54 years after the initial time is how we get that 66 million, right? Okay, so now, time to solve for K. So we have to remember how to solve an exponential function, don't we? An exponential equation. Okay, let's see what you remember. What's the first thing I got to get rid of? Good, the 31,000. So I'm going to divide both sides by the 31,000. And gratefully, and I know it's not going to come out neat in the calculator, but gratefully I can at least divide by 1,000 and get rid of those 3 zeros, can't I? Okay, then what? Yeah, I got to get rid of the E next. How do you do it? Excellent. Take the natural log on both sides, which means I'm going to end up with the natural log of 66,303 divided by 31 equals, what happens when you take the natural log of an exponential base E? Good, they cancel out, which means you're left with 54K. Agreed? And to get the K by itself, yep, you divide both sides by the 54. Zoop. All right, so they ask us to round to 3 decimal places. You do your rounding, I'll do my rounding, and hopefully we come up with the same number. And if we don't, one of us did the finger punching incorrectly. But I end up with K as 0.142. Did you get the same? All right, which means my specific formula for this problem, remember, to write the specific formula, I need the initial amount and I need to know the K. And since the K is positive, I know it's a growth rate. Good? All right, let's see what Part B has in store for us. Part B would like us to find the cost in 2008. How do you think you're going to find the cost in 2008? Yeah, you're like, plug it in. Yeah, plug it in. There's my specific formula. But wait, what's time? Okay, good. The initial time was 1950. That was t equals 0. In 2008, time is going to be what? Good, 58. So, the value after 58 years, or at year 58, shall I say, right? We're going to plug in that 58 for the t You do your finger punching. I've already done mine. Hopefully you and I come up with the same thing. And if you're like, that's too big, that's the right number, because I got an exorbitant amount of money also. Whoops. It would be helpful if I wrote the correct number, don't you think? Okay, so I ended up with 117,006,795 because this is still money and 10 cents. More than likely they'll have us round to the nearest dollar. So anyway, so it'll be $795, won't it? Yeah, that's a lot of money. When it sold for $31,000 in 1950 and 58 years later it's selling for $117 million. Hindsight is 20/20, isn't it? Would have been great to have known that. Okay, there's a part C here. Part C would like us to find the rate of change in the year 2000. Okay, well, in order to get the rate of change, what do we need to have? Yeah, we need the derivative, don't we? I don't have the derivative yet. I got the original function, but if I want a rate of change, I need to find the derivative. So, what are you going to do? Good. To take the derivative of an exponential function, the derivative is itself, right, multiplied by, good, the derivative of the power. So, this is the original part, isn't it? So that's just our original v of t, isn't it? And you're multiplying it by, good, the 0.142. Well, v of t was this $117 million, wasn't it? So if you take that $117,695.10 and you multiply by the 0.142, I got, we'll see what you get, but this is what I got. I got that we have $16,614,963 because it's still a value, and 49 cents. This is the change per year. This is the rate of change per year. That's a lot of change. $16 million change per year, that's a lot of change. That's a large rate at year 58. Got it? Okay. There is a part D, and in order for me to do part D, I need to erase the board a little bit. So as I erase the board, I'm going to just kind of talk about part D. Part D wants to know how long it's going to take for that painting to sell for $8 billion. You're like, you're kidding. I know, right? Can you imagine paying $8 billion for a painting? I don't know that I would do that, to be honest with you. Some people would. Kind of not in my wheelhouse, but that's okay. It's in some people's wheelhouses, right? Now, let's get part D up here on the board. Part D says, how long after 1950? Will the value be $8 billion? And $8 billion, if you're like, how do you write? That's got those 9 zeros after it. All right, so they want to know how long. So if they say how long, that means you're searching for t, aren't you? Remember, here's our specific formula. So in our specific formula, I'm searching for t, which means I better know the ending balance, right? So what would the ending balance be? Good. The ending balance is at $8 billion. So how do I start setting it up? Okay, I heard you. 8 billion make sure you have the proper number of zeros, equals 31,000 times e to the 0.142t, right? Okay, what are you going to do first? Good, divide by the 31,000. And when I do that, do you notice that you can at least divide by 1,000 and get rid of those last three zeros, right? Okay. Then what? Good, I got to get rid of the e. So to get rid of the e, natural log it on both sides. So I'm going to end up taking the natural log of 8 million, because remember I canceled these three zeros, so to speak, by dividing by 1,000, over 31 equals the 0.142t. Then what? Good, divide by the 0.142 on both sides, right? Okay, so this is where you really have to be careful of your finger punching, right? I don't do any of my calculator work until the end. So the first thing I'm going to do, and this is what I would do, I would literally do 8 million divided by 31. Then take the natural log of that number. And remember, you're using your graphing calculators, so there's nothing you need to erase. And then some of you are punching it in all at once in your graphing calculator. That's fine. Whichever way you want to do it, be my guest. I always work the order of operations. I would do this parenthesis first, get that answer, take the natural log of this answer, equals, and then take the answer and divide by 0.142. So, let's see if you and I agree. I got t was approximately 88 years. Okay, so 88 years after 1950. So what year would that be? So if we have 1950 plus that 88 years later, yeah, that looks like the year 2038. All right, well, what are we now? Okay, so at the time of this recording, we're in the year 2021. So let's see. 17 years. We'll wait and see. Stay tuned. Got another one.